Hello and welcome. In this video, I'm going to show a demo of principal component analysis. Principal component analysis is one of our go-to dimensionality reduction methods. And so we've talked about regularization, we've talked about feature selection, but what do you do in cases where you have, say, thousands of features, maybe even 1 million features? It's very hard to do, say, feature selection on a case like that. In fact, it's pretty much not going to work. So what we want to do is find some kind of coordinate transform that we can use to project the most important features. And that's what principal component analysis does, as do other algorithms. So let's start with a simple example, and then I'll show you applying this to some real-world data. All right, so on my screen here, I'm going to compute from the NumPy random package, I'm going to compute a multivariate normal. So I need to specify a mean and a covariance. So my mean is going to be 0, 0, 0, 0. So it's a two-dimensional bivariate normal. And then here's my covariance matrix. It's got unit variance on each axis and a correlation between the two variables, or covariance of 0.6. Okay, and we'll go ahead and compute that, and you see I wind up with a 100 by 2 NumPy array, and I'll go ahead and plot that. So we just have a look at what the outcome is, and it's not basically what we'd expect. You see there's a almost elliptical arrangement of the data with a few outliers. The variance should be identical on this axis and on that axis. And that's all by design, and you can see there's this fairly strong, covariance between the two dimensions. So we can now compute using the scikit-learn dimensionality reduction package, which I call SKDE. We're going to compute PCA object. We're going to then fit that to this sample. This is what we're calling our sample, these data here. And then I'm going to print the explained variance ratio. And we only have 2 dimensions, and you see that the explained variance ratio adds up to 1, which it should do, 0.85 plus 0.15. And so you can see that the first component explains about 85% of the variance. The next component explains only 15% of the variance. And that's the sort of thing you want with principal component analysis. You want the higher components to explain a lot more of the variance than the lower components. So we have to scale the actual rotations or components themselves if we want to look at them. And we scale them by the explained variance ratio. So that's what I'm doing with this code. And so now I have this components vectors here that are scaled. My first principal component, my second principal component, and a little bit of funny matrix manipulation there, but I can go ahead and make a plot. And you see that first principal component, it does really seem to line up right on that major axis of the ellipse, and it has a fairly long arm compared to the arm of the second principal component, which is pretty much along the direction of the minor axis of the ellipse. So those are, well, the plot looks a little skewed, but they should be orthogonal actually, and so you can see a lot more variance explained along this direction than along that direction. So that's very promising. And then we can apply from the fitted PCA model, we can apply the transformation to that sample and plot that result. And you'll see what comes out of that. And you see, okay, So along this axis, we have most of the variance. And you see the scale is from about minus 2.5 to plus a little, 2.8, almost 3. So there's a lot more variance on this direction. And you look at the scale here is an order of magnitude less, roughly, which is about what we expect, right? Because remember what our variance, the ratio of those variance explained were. So it looks like we've effectively transformed to a new coordinate system here, this new dimension 1, this new dimension 2, where there's a lot more variance along dimension 1 than dimension 2. And we've done that effectively by rotating this original data to this new coordinate system. All right, so how does this work with some real data? So I'm going to load the credit features and credit labels. And they've been scaled and all that. And then I'm going to break them up into a training and test data set using the usual method here. All right, so now I'm going to create a PCA model for those, for my X-train. And notice, I do it on the training data set, not on the original complete features, and I'll wind up with my principal components. All right, you can see some hyperparameters there. And then I'm going to print a few of the attributes of those objects there. And you'll see. So this is variance explained, and you see the first one is about 21% of the variance, then about 15% of the variance, about 13% of the variance. So you see it drops off pretty quickly down to numbers that are effectively 0 down here, 10 to the minus 32 and 10 to the minus 33. But if you add it all up with numpy.sum, you get 1.0, which is exactly what you need to get because you need to explain 100% of the variance. But you can see that pretty quickly you reach a point of diminishing return as to how many of these components actually explain useful parts of the variance and which ones are just explaining noise. Remember, the data is always noisy, so even a component like this that's 4 orders of magnitude smaller than a component there probably is just explaining noise and not real information. And we can visualize that with what we call a scree plot. And I've created a little function here called plot underbar explain to make a scree plot. Let me run that. And so it's the variance explained versus component number. And you can see there's a knee here at about 4 or 5 components. And then it continues on down. So the question is, where's your cutoff? We could try it around the knee. We could take a little more. We could go even down to here. We definitely don't want these components that effectively explain 0 variance. That's just noise for sure. So then, okay, so what do? So we can create a subset of our features, and this is the crux of the whole method. We wind up with a smaller feature set. If we say took the first 5 components, I'll show you what happens. So now we have 700 training cases, and we've just taken the first 5 components, which you can see explain a fair amount of the variance. That might be too extreme, given that there's still some noticeable slope, some noticeable variance explained here. But at some point, we'll pick a cutoff, and that's how we get the dimensionality reduction, by picking that cutoff. So we've gone from 35 to maybe 5 or maybe 10 or 15 features, but these new features, these new components are in that transformed or rotated space. So that's the idea of the dimensionality reduction with principal components. And you can, this method is computationally very efficient, so you can apply it to very large data sets with very large numbers of features and get down to some manageable number of features.